Hello and welcome everyone. My name is Alex Proskurin and this is the third part of our lecture series in financial machine learning, which is called modeling. So in the first lecture, we have discussed how to generate various financial data structures, which can be used to generate features, etc., how to deal with multi-product series, how to build imbalance and standard bars. On the second lecture, we have discussed how to label financial data sets, how to apply trend scanning, triple barrier, matrix flags, and tail sets labeling. And now we can move to modeling. So in this lecture, we will discuss such topics as label concurrency, cross-validation, sample weights, bagging versus boosting techniques, and actually how to set up a bagging classifier or random forest classifier if you would like to solve financial machine learning type of problems. But let's start with label concurrency. And this concept is extremely important in financial machine learning because it is used in so many algorithms and cases when you try to build financial machine learning model. So let's go back into triple barrel method and briefly discuss what are the consequences of this type of labeling method. So let's imagine that we have a security and the green dots correspond to times when our signals were generated. So basically, green dots are our filtered events. But now let's discuss how we can label those type of events. So let's, for example, use very tight fixed profit and stop loss levels. So as we have discussed in the previous lecture on labeling, we call them fixed profit and stop loss levels, but actually they are just upper and lower horizontal barriers. So we use a quite small volatility multiplier to set up those barriers. And as a result, we can see that the time from time when the label was generated and time when we know the exact value of label is relatively low, because when you have very tight fixed profit and stop loss, you don't need that much of price fluctuation to understand the label value, right? So here we can see that all of our labels do not overlap. So what we call overlap, meaning that if, for example, time when the label was generated and time when the label was labeled, so meaning that time when we understood the label value, meaning that either one of the barriers was hit, in that period of time, no other label was not present. So as we can see here, we call it sample, which was filtered. And here we have time when we understood if the label value is -1 or 1. So here the label value is -1, and we understood it at this point of time. For this label, we understood it at this point of time, and the same goes for other labels. So let's fix various definitions. So the time when we understood the value of the label, we will call it T1. And it is how it is called in Marcos Lopez de Prado book, Advances in Financial Machine Learning, and in MLP Lab documentation, you will see the reference to T1. So basically the T1 is a time when the label, when we understood what is a label value. So actually for triple barrier labeling, T1 is the time when one of the barriers was hit. But now let's take a look at relatively narrow fixed profit and stop loss levels. So let's use much wider horizontal barriers, meaning that we used bigger number of volatility multiplicators to set up them. And now what we can see is that labels start to overlap. What does it mean? Let's take a look, for example, the first label. So here it was generated and we set up both fixed profit and stop loss levels, and we understood the time when it was generated only by this time period. However, by that time, we already have generated the second label. So in this case, these two labels overlap because starting from the time when the first label was initiated and till the time when we understood what is the first label value, in this time period, we have generated another label. So in this case, we say that label 1 and label 2 overlap. So as we can see here, these labels start to overlap. And that actually creates lots of problems in financial machine learning. Because in this case, we cannot say that we have IAD data, so independent and identically distributed, because, for example, first and second label use the overlapping amount of information. In this case, we start facing autocorrelation type of problems. So we can actually imagine label concurrency in a small diagram. So let's take, for example, label which was initiated at time t1, and we understood the label value at time t5. The second label was initiated at time t3, and it was generated at it was labeled at time t8. The third label, the blue one, was initiated at t4, and we have understood its value at t6, and the final label was initiated at t8, and it was labeled at time t10. So as we can see here, the black label overlaps with both blue label and red label. What we can also see is that red label overlaps, of course, with black label and blue label. And the blue label also overlaps with all three red, red and black labels. And only green label does not overlap with any one of them. So let's keep that in our mind, the concept of label concurrency, which we will understand how applied further in our modeling. So now let's take a look at cross-validation techniques which are applied to solve financial machine learning type of problems. So consider the following problem. At certain times, the machine learning model has to make predictions resulting in certain actions. So we enter the position, predict the price, the trend direction, we buy the security or sell the security, and see what's going next until one of the labels was triggered. At later times, the response computed from the results of the actions are known. So this is the statement of financial machine learning type of problems. So the first thing which may come to our mind is to use a quite well-known cross-validation method, which is called K-fold cross-validation, meaning that we split our data sets into, for example, K-folds. That's why it is called K-fold cross-validation. We fit our model on the train set and see the out-of-sample score on test set. So here on this slide, you can see the graphical representation of K-fold method. But here we have actually some problems which we start facing if we use K-fold cross-validation. So the first thing that we face is that time series data is time ordered, of course. And in real world applications, we use past observations to predict future observations. The second problem is that time series data is often strongly correlated. And one of the reasons partially for that is label concurrency, because when your labels overlap, they are not IID because they use the same piece of information to generate label values. In the third, observations cannot be assumed to be drawn from an IID process as a result of serial autocorrelation and concurrency. And as a result of that, leakage takes place when training set contains information that also appears in the testing set. So let's take a look at the previous picture to understand what is leakage. So let's take a look at this example. So let's imagine that we used, for example, this data, which includes the first 3 data points to train our model, and we use out of sample data to understand what is the out of sample score. So on the one hand, there is nothing bad in that because our data is our faults are time ordered, right? So we train on the first 3 points and estimate the performance of our model on the next 3 points. But here there is a small nuance which comes in this situation. So as we can see here, the time when the third label was labeled leaks into our out of sample period, and time when the second label was labeled also leaks out into our out of sample period. So in this case, we have an information leakage because we cannot see that vividly, but actually because we need to take a look in the future to understand the label value, despite the fact that we use features in our train set to train our model, we actually have leakage because we do use the information from the future, from our out of sample set, in order to label our labels in sample set. And that's why K-Fold's cross-validation fails in finance in the way it is implemented in classical setting. So one of the ways how we can solve the problem of K-fold cross-validation. So if we take a look at the in the internet to understand what kind of cross-validation scheme is present to cross-validate time series data, the answer is walk-forward cross-validation. So how walk-forward cross-validation works? So we train our, let's take a look at this picture. The yellow line corresponds to train test. So here we train our data on the first period and we test our data on the following period. After that, we include, we add more data to the train period and shift our test period. In this case, we can actually cover the whole test period in our walk forward cross validation. So as you can see, if you sum up all these black bars, you can see that actually you cover almost all timestamps in your data set. What are the pitfalls of walk forward cross validation? So near the split points, we may have training sample whose evaluation time is posterior to the prediction time of the validation set samples. Such overlapping samples are likely to be independent, leading to information leaking from the train set into the validation set. And that's actually what we have discussed on the previous slide when we showed that actually, despite the fact that you time split your data, you can still have a leakage of information. So on the picture with green samples, when we train on the first 3 samples and test on the last 3 samples, green samples, we saw that actually we do have this leakage, but it is not that vivid as it seems to be. So it is impossible to make KP ratio very large, leading to large variance in the performance statistics. So let's go back into the picture which describes walk forward cross validation and understand what is the KP ratio. So KP ratio is the ratio of our train data and test data which is used to estimate the performance of our algorithm. So as we can see on the first fold, our train length and test length is pretty much the same. So, and when we start increasing our train sample lengths, we see that this ratio starts to decrease. As a result, the variance of our estimate will be very large. Firstly, and secondly, there is a problem that on the first folds, the algorithm may not have enough data to train. As a result, your out-of-sample score will be relatively low, not because your algorithm is bad, but just because you don't have enough data to train your algorithm. And the most relevant part of our data set, namely the most recent one, is also the one which is used least. This can be a problem for time series subject to regime changes over long periods of time, as it is often the case in financial time series. So if we take a look at the picture one more time, we can see that the most recent part of data set is used the least number of times because we will just train on this on this data and test on this data. So And that's why it is so our algorithm will be never trained in work forward cross validation, uh, because we just use the most recent data as our out of sample estimation data set. So what can be the algorithm which can both combine the power of K-fold cross-validation and still solve the problem of information leakage? And that's actually where purged K-fold algorithm comes in action. So what this algorithm does, it still uses the framework which is proposed by K-fold's cross-validation, but why it is called purged is that we will purge and delete those samples which have T1, meaning that the time when the label value is understood, present in our out of sample test. And we will also purge those observations from test set which may be present in train set. So when the label is stuck between train test and test set, meaning that the label was initiated in train set, but the label value was only understood at the timestamp in test set, these labels will be purged, meaning that they are deleted from our both train and test, and they are not taken into account when we evaluate the performance of our model. So that's actually how K-fold works. Some people may say, but you still don't solve the problem of that financial time series is time ordered, because at the end in K-fold cross validation, you still use your, for example, future data to estimate the time period before the future data. And here, what we can answer why Purged K-Fold is still extremely efficient is that actually financial markets, on the one hand, are time ordered, but on the other hand, financial markets have various regimes which may repeat each other. And instead of trying to understand how the performance of your algorithm improves or decreases with time, you would rather like to understand how the performance of your algorithm improves or decreases with various regimes. So, for example, your 2020 market pullback can be relatively similar to, for example, 2008 crisis, which is actually not. But what you can do, you can compare various regimes between each other in the past and understand how your algorithms work in various regimes, meaning that bull market, bear market, or sideways market. So as you can see here, compared to K-fold, we purged those observations which have T1 present in our test set. So here we will purge those observations if their T1 is present in test. So here we will purge those observations which started in test, but they have present timestamp T1 in train. So even if T1 is present in train, but the label starting point is present in test, we will purge this observation. So purging comes in action if either label timestamp is present in train or test and T1 is present in train or test. So we don't want our samples to overlap. So we can see this on this great visualization, how purging is applied and how it can be visualized. So going back to our example with this sample, what we will do is that this label will still be in our training set. The second label, as it is not in our test it is not in our test set. So let me see that it is not in our test set. It will be preserved, but the third label will be purged because its time T1 goes into our test set. So the third label will be deleted from our from our train set because its T1 is present in test set. So now let's go a little bit deeper into Purged K-Fold. If you would like to add an extra layer of, I would say, regularization, so if you want to be triple sure that you don't have information leakage in your cross-validation scheme, you can apply Purged K-Fold plus embargo scheme. So what embargo does, it just strictly deletes, for example, 1% or 2% of samples before our train set. So in this case, you can even more preserve the time structure of your data, meaning that if you have train set, you have test set, you delete those values which you purge them, which have the T1 present in test set, but you can also embargo, for example, 1 or 2%. Actually, one of the I would say common used setup is to embargo 1 or 2% of your data set before the train set. So in this case, if you have train and test, you will delete a small number of data points to make them even more, even to divide them even more. So in this case, you will be quite sure that you do not have information leakage in your data set. So that's actually how Purged K-Fold embargoed cross-validation scheme works. And now let's take a look at the documentation of Amalfi Lab to understand how this function is applied. So if we go to modeling, we can see the cross-validation section here. So let's take a look at the class which is called Purged K-Fold. So the first thing which we need to understand is that Purged K-Fold uses sklearn cross-validation API. So that's why Purged K-Fold can be used with standard sklearn functions like bagging classifier, random forest classifier. So it has the same API and function calls as every cross-validation scheme in sklearn package. So here we have nsplit. So this is the number of folds which corresponds to K-fold method. And the second time series are called samples info sets. So if you remember, we have agreed that we have time when the label was generated and time when we understand the label value. And we called it T1. So actually samples info sets is a panda series which has indices of your labels, time when labels were generated, and values of these are times when we understood what is a label value. So for triple barrier labeling, samples info sets indices will be the filtered indices of our samples, of our labels, and the values will be the T1, so the time when the first of the barriers was hit. So the Purged K-Fold algorithm needs this information, which is called samples info sets. As you can see, you have the PCT embargo. So this is the percent of data which is deleted before the test set if you would like to use the embargo scheme. So as you can see, by the default, the embargo value equals to 0. But as we have discussed, like it is well known and used guideline to use either 1% or 2% of your data to use it in embargo. So what we can see here, it has the same API as in sklearn. We have split method, which takes x and y as inputs and generates the group, the folds of your purged K-fold embargoed cross-validation scheme. In the next lecture series, we will discuss how sample weights are used in financial machine learning and why using sample weights is so important to use in those fit and score function calls.